In this video, we're going to be talking a little bit about the EM spectrum, the electromagnetic spectrum. And I think some people get this one complicated more than it has to be. So just remember, when we're thinking about this, remember, it's always going to connect back to just light. That's all we're dealing with here. But we'll have to think about other types of light than we are normally accustomed to. So let's dive into this. So the EM spectrum has a lot going on here. And when we first think about light, probably most of us start thinking about what we are engaging with most frequently, and that is visible light. But visible light only makes up a very small fragment of the electromagnetic spectrum. It is just electromagnetic waves that have a length between 400 nanometers and 750 to 800 wave numbers, depending on who you talk to. So that's all we're talking about here, light waves. We know it's an electromagnetic wave. It has those two components. We're not going to really care about those components, but we're going to need to be able to quantify it and be qualitatively talking about it knowledgeably. So that's what we need to have set for here. So there are quite a few different segments of the electromagnetic spectrum. So we talked about visible. If we go to the left here, we find out we have ultraviolet here. And if we look, this is now getting to be smaller in wavelength than what we saw in the visible. We can go to smaller wavelengths to get to the X-ray or down into gamma rays. So as we go to the left here, we're going in decreasing size of our waves. But there are other things that we should think about. We could also think about, for example, the energy of our wave. And what we know is that gamma rays down here again are the most energetic part of the electromagnetic spectra. X-rays are less energetic, and so on and so forth. On the other side, we have things in the electromagnetic spectra like infrared. So most of us think about this connecting with heat radiation. And we also have radio waves. So things like, what you'd have in your actual FM radio or in your TV if you were still using broadcast. So that is what we have there. There is one more spectrum that I'm going to add in here. And we're going to say it's kind of in this region right here. And this is MW, which stands for microwave. You can probably take a guess where you've interacted with microwaves before. Yeah, it's the same thing that's used in your kitchen to heat up your leftovers or heat up your tea in the morning. So these are all just the different segments here. Big things you'll want to know about this is definitely the trends for thinking about the increase or decrease of wavelength, the increase and decrease of the energy. But also, we can do this more quantitatively. Over here, I have some equations that we can look at. So, for example, the primary one here is that the energy of an electromagnetic wave, of a photon, is given by the frequency of that photon times this constant h. And h is Planck's constant down here. That'll be on your equation sheet, so no need to memorize it, but you can if you want. It's kind of a funky value, 6.626 times 10 to the negative 34th joule seconds. And when we're thinking about frequency will have units of inverse seconds here, which we haven't really talked about, but it is a connection. So it's another way of thinking about quantifying the system of our electromagnetic spectrum. If we want to connect it to things like the wavelength, which is commonly denoted by lambda here, we can use this equation, E equals hc over lambda. So h again is Planck's constant. And now we're using c, which we should probably recognize as the speed of light. Definitely use all those sig figs there. You never want to be limited in. If we just need to convert between wavelength and frequency, there's a simple relationship given by the speed of light here. The speed of light is always going to be equal to the wavelength of the photon times its frequency. So that's an easy way to convert between those two when you need to. One other tidbit that's going to come in handy that I'm going to remind us about here, down here, this is something we easily forget. The mole is a concept we've used forever in chemistry. But it applies to photons as well. We can think of photons as a physical thing that we can count up. So if we have a mole of photon, just recognize that that means there are 6.02 times 10 to the 23rd photons. That'll come in handy in some of your dimensional analysis calculations. So don't forget that conversion factor. When we actually want to differentiate different wavelengths or different frequencies, there's a number of methods that we can use to do this, but probably the most simplistic one, the one you've probably seen before, is use of just a basic prism here. So here I've got a prism of glass, and on the left-hand side here, I've got some white light coming in. Maybe this is just radiation from the sun that we're getting in, and as we pass it through our prism, we see that it will break up. And it breaks up in a very characteristic fashion. The low energy is down here. We see the red is always here. We see slightly higher energy with yellow frequencies in this region. We've got higher energy green radiation, followed by blue here towards the top. So it always breaks up in that characteristic way when it goes through a prism. And this is a common tactic that we use for spectroscopy. If you want to know more about spectroscopy, take instrumentation. Hopefully a couple of you remember this from the instrumentation course. But yeah, so if we bring white light in, we see our usual color spectrum of the Roy G. Biv over here that we're kind of used to. And this is useful because we can make measurements of this now. Now, when we break up white light, we get what we call the continuous spectrum like we have here. So here I'm just breaking up white light. So we see our violet, we see our blue, we see green, yellow, and red here. And so that orange would be somewhere in here. So there's our Roy G. Biv, if you want the indigo in there. This is what we call a continuous spectrum. There are no gaps in it. There is a color that is always there, and you can see that it is continually changing as it goes through there. We're going to see in a later video that we have things that we call discrete spectra. So this discrete spectra here is where we don't see all of the frequencies, we just see a few. So in this case, I've got something down here by the red, I've got something in kind of that light blue shade, something kind of in the indigo, and something in the violet here. And this is what we see oftentimes when we look at elements. They don't produce white light if we start exciting them. They actually produce something very different. We'll talk about why that is in another video. But what is important to recognize at this point is that by controlling the chemistry that we're looking at, we can actually produce different colors of light. So here I've got some examples that I'm sure you've seen somewhere. These are just neon signs. So this is the classic old theater here that had the neon tubes, very popular back in the 50s and 60s, not as common nowadays because of their energy usage. These types of lights are really inefficient, but they produce some really interesting colors to us. Another place you might have seen these types of emission spectra where it's a discrete color that we're getting out again is in these signs that you see often at bars and restaurants, the neon signs as we call them, because the light often is being generated from elements like neon. So you've definitely seen these all around. They're part of our world. And we'll have to do a little bit more digging to understand why we get the colors that we see out of them. But definitely that's part of the electromagnetic spectrum. We can use the chemistry to control whatever color we want to see. All right, I think that'll do it for this video. As always, if you have questions or concerns, let me know. We can talk about it in class, whatever you need, so give me a holler. But until I see you next, be excellent to each other.